Today we're going to be talking about Fourier series. First of all, we need a proper definition for these, so we actually know what we're talking about. Now, broadly speaking, they are an infinite sum of sines and cosines which converges to a given periodic function. Or, more formally, we can just say that f of x is an approximation of this infinite series, where a sub k and b sub k are coefficients which are given by the following two equations. The function is periodic. In this case, the period is 2 pi, but we can and will later on see that we can change that. Also, rather clearly, the integral of the function must be defined. Any function that is integrable has a Fourier series, which is very nice. But more importantly, why would we want to transform any function into an infinite sum? For one, there are certain functions that are more difficult to work with, such as piecewise functions, and if we expand it into its Fourier series, we only need to work with one expression, which we will see later on. However, there is actually a much better use for it in the real world. Almost any kind of wave can be written as a sum of sines and cosines. So for example, we can find the Fourier series for a recording of somebody's voice, which is a wave. So one of the many applications is compression. You take the sound and expand it into its Fourier series. Most of the time this will be an infinite series, however, it converges so quickly that taking the first few terms is actually good enough to produce the original sound. Simply talking about it is pretty cool, but a little hard to believe that all of this is possible with sines and cosines. So we need some graphs to get a better picture. Here we have the function, the equation, f of x equals x, and its corresponding Fourier series. We can see the period is 2 pi here, from negative pi to pi. And here we are only using the first 5 terms, and it's already pretty accurate. And the Fourier series is given by this series. Now if we add the next 10 terms, we get a much better approximation. And we only have to store 15 terms, which is pretty good, and obviously it converges quickly. Now, what good would all of this do if it only works on the interval from negative pi to pi? Well, luckily enough, we can change that. Like we can change the period of sine of x by writing sine of 2x or sine of x over pi. We can do the same for Fourier series. The value of L here determines the period. Now this is the function e to the x, and it's very massive, regardless of whether or not we have the changing period. And I just wanted to show a more unappetizing example of a Fourier series. In this case, L equals 1, and the interval goes from negative 1 to 1, and the period is 2, or 2L. Now simply changing the value of L changes the period. Here, L equals 2, and the period is 4. It's the same function, all we've changed is the value of L. Now, depending on the range of values that we need to approximate, we can simply change the value of L. And it is fairly reasonable to do this for any Fourier series. Now, as I've mentioned earlier, we can also find the Fourier series for a piecewise function, which sounds pretty cool. This one, f of x equals x from 0 to 1, and it equals 1 from 1 to 2. So x here and 1 here. This is obviously a pretty powerful tool. We can change a piecewise function into one expression, which certainly makes it easier to work with. But after all of this, and all of these examples, I mean, the computer is drawing them, but it still seems pretty unbelievable. So I'm going to try to relate it to something else that more people have been exposed to, which is probably Taylor series. These are infinite polynomials. The green here is the Taylor series for sine of x, which is shown in orange. Sine of x is shown in orange. We can see it diverges, and it becomes a terrible approximation for values greater than pi. However, if we increase the number of terms, we do not get a better approximation like we do in Fourier series, but rather a greater range for which this series is useful. Here we have the first 15 terms, and the approximation works for a much greater domain. Compared to here, where it's just about from negative pi to pi, here is much larger. Now, in the case of Taylor series, the error is pretty small, in a neighborhood of the point where it is computed, while it may be very large at a distant point. So in the case of the Fourier series, the error is distributed along the domain of the function. For Fourier series, we can simply increase the period so that our approximation has a larger domain, which simply means changing the value of L. For Taylor series, we need to add on more terms, which can become a little more expensive. The trade-off is a better approximation. The important part here is that they are both infinite series, and while the details are different, they both approximate very well. And it's easier to visualize a polynomial converging, so I think it's useful to relate Fourier series to Taylor series, just so we kind of understand what's going on. But keep in mind that they do not act in the same way. Well, that's all for that. By the way, sines and cosines also make for kind of beautiful pictures. I hope you enjoy it. Thank you very much.